Bismillahirrahmanirrahim. Hello and welcome to Rahman Digital Production. This is the series of videos in which we are talking about the physics 5054, and this is lecture number 28. Ladies and gentlemen, in the last lecture, we studied that how we will find the center of gravity or center of mass of the regularly shaped objects. Today, we are going to determine how to find the center of gravity or center of mass of the irregular shaped objects. Let us do that with the help of an experiment, and then we will derive a conclusion. The topic name is center of gravity or center of mass of irregular shaped objects. For that, we need retort stand, a scale, and a thread, a bob, which is called plumb line. And you might have seen when the masons are constructing the walls, they are checking again and again that whether the wall is straight or not. This plumb line is that thing. So this is shown from a side. When we are taking it from the front, then it will look like this. This picture is from the side. Ladies and gentlemen, this is known as plain lamina sheet, which is of irregular shape. This is not regular shape as you can see from the shape. Now first you have to do what? You have to make 3 holes near the edge of the lamina, and which must be apart from each other. One thing more you have to keep in mind, that these holes must not be very large, so that most of the mass of lamina should go away. No, it should be a small hole. So these holes should not be nearer to each other. It should be far apart from each other. Now hang this lamina with the help of a pen, and when the plumb line is stable, it is not moving, then draw a straight line with the help of that scale. You have to draw a straight line, then you have to remove this, and you have to put this hole inside this pen, and again you have to draw a line with the thread of the plumb line, and similarly you have to put this third hole inside this pen, and when this plumb line is stable, then you have to draw a line. Ladies and gentlemen, wherever these 3 lines intersect each other, that will be the center of gravity. So in this particular case, it is here. So in this way, you can find the center of mass or center of gravity of irregular shape objects. You have to keep one thing in mind, ladies and gentlemen, that whenever you are putting this lamina sheet in the pen, so it should move freely. It should not be pressed with the pen, so you cannot move. It should. These are the two precautions you have to take while performing this experiment. The hole must not be that much bigger, and the sheet must be hanged to move freely. So in this way you can find the uh, center of gravity or center of mass of irregular shape objects. Now we are turning our focus to a very important topic, and that is stability or equilibrium. Ladies and gentlemen, uh, this is the last topic of this chapter. Then we will turn our focus to the exercise. Very important. So let us study the stability or equilibrium. Ladies and gentlemen, this stability is very closely related to center of mass or center of gravity. Stability is the ability of objects to regain its original position when slightly tilted. Uh, we can explain this phenomena through these diagrams, and then you will understand that there are three types of equilibrium or stability. The first one is stable equilibrium, the second one is unstable equilibrium, and the third one is neutral equilibrium. So let us start with the first. This is a paper cone, and this is a table providing the support to hold the paper cone. Now in this particular case, the paper cone is on the table. There are two forces acting. One is the weight of the paper cone, which is downward, and one is the contact force R, which is provided by the table. Because the line of action of the weight is equal to, in the same line, is into R, so they are cancelling the effect of each other and they are in stable equilibrium. Once you tilt this cone a bit, so you can observe that the center of gravity rises and then falls back. uh, when you are tilting it up, and after the release of it, it will come to its original position. Note two things: that the line of action of W is inside the base. If you can see that this line is inside the base, until this line of action of W is inside the base, it will come back to its original position. This is if you are tilting it more and this line of action is coming out of this base area, so it will topple down and it will never come back to its original position. Ladies and gentlemen, uh, one thing we noted that the center of mass is raising and then it is falling down one. The second one is that the line of action of W remains inside the base area. And the third thing is that the anti-clockwise moment of the weight, making it possible that it will move back to its original position. So in this case, this is stable equilibrium. Stable equilibrium is that type of equilibrium in which if the body is tilted slightly and it uh, comes back to its original position, that is a stable equilibrium. Now in the second case, the paper cone is at the point of contact and the center of mass are in same line, so they are cancelling the effect of each other and this is in equilibrium. But if you tilt it a bit, it will topple down and it will never come back to its original position. Here we are observing the two things. The first one is that the center of gravity is lowering, is coming down. In this case, it was rising, but in this case, it is lowering than the original center of gravity, the time at which this cone was in equilibrium. The second thing we are noting that the line of action of W is out of the base. In this case, it will not come back to its original position and it will topple down. This type of equilibrium is called unstable equilibrium. One thing more I should mention here, that clockwise rotation of the moment of weight is allowing this paper cone to topple down. Uh, Third is the neutral equilibrium. If we are putting this cone in this position on the tabletop and we are rolling it, it is rolling from here to here, just like we are rolling it here and it comes to this position. Ladies and gentlemen, you have to note two things here. One is that the center of gravity neither rises nor falls. It remains at the same position. And the second thing is the base area is very wide and this G or the line of action of W is not getting out from the base area. So it means it will remain always in equilibrium. It will not topple down, not it will regain to its original position because we have not tilted it. We roll it, or if we are shifting it like this from here or from this to here, then in both cases the center of gravity remains at its position. So this type of equilibrium is called neutral equilibrium. Ladies and gentlemen, for equilibrium to take place, there are two very important phenomena you have to observe. One is that the base area must be wide. Here in this case, the base area is not wide, so it is not getting any equilibrium. Here the base area is more, so it is coming back to its equilibrium position. And in third case, the base area is much larger as compared to these two cases. Ladies and gentlemen, the second thing we have observed in these experiments, that if the center of gravity is rising, then it will be unstable. If the center of gravity is lower, then it will be in stable position. That is why the racing car area is made very wide, so it will be in equilibrium when it is turning uh, a road, in a road. So the one thing, and if you can observe, these cars are very nearer to the earth. It is not up, because then the center of mass will move upward and it will topple down when uh, crossing a curved road. So that is why they are made very wide. This area you might have observed this during the car racing tournaments. So here one thing is the center of mass is lower, and the second one is the area is wide. If these two qualities are there inside any object, then it will remain stable. Otherwise, it will not be that much stable. Uh, for that stability or equilibrium, you have to find the center of mass, and you have to balance that with the weight. There are balancing toys. You might have seen that the beak of that bird is with a pole, and when you are pushing it down, it going up and what, but not toppling down. That is the example of equilibrium as well, because all the mass of this bird is acting at this point, the point of contact. So this is balanced by the contact force which is upward on this bird. So if you are pushing it down, it is doing like this but not toppling down. One example more I want to give you, which is not in this book. Have you ever seen that a person is crossing one building to another building while walking on the rope? That person is also using this stability rule. They are having a stick in his hand, and they are doing that stick like this, and through this stick they are balancing the body with the reactive force acting, or the gravity which is acting on him downward. So that is also an example of stability. The third example is that these are the lead weights. This is a cock and this is a needle. On a needle tip, they are, if you are topping it like this, then it is coming back to its original position. This is needle, this is cock, and these are the lead weights. So this is also the example of stability. This is not a magic, but using the principles of physics. So, always when the magicians are performing different tricks, actually they are using the physics principle. Physics is such an interesting subject that it is used all over around us. We learn, and this is the nutshell of this topic of this chapter, that the stability of an object can be increased by lowering the center of gravity and increasing the base area of the object. Okay, this is the end of theoretical portion. Now we are coming towards the exercise of this, and we will utilize our knowledge we gained in the theoretical portion, and we will see that whether we are being able to solve these questions or not. The first question, which is at page number 77, they given this diagram, and they are saying a door require a minimum of 32.5 Newton. So F is equal to 32.5 Newton. We are writing the data as well. In order to open it. What is the minimum distance of the handle from the hinges if the door is to be pulled with a force at the handle not greater than 50 Newton? So here it is torque, and then we have to find the D, and F is greater than how much? It is given as 50 Newton. So if you see this as torque is equal to F cross D, then we have to find the D, then D will be the subject, and torque divided by F. So now we have to put the values 32.5, and then we have to write 50, and that will be meter. So when we calculate it, it comes out to be 0.65 meter. 0.65 meter, and the B option is the correct one because this option is given. So the B option is the correct one. Now the second part is saying a driver's foot presses on a pedal in a car with the force of 20 Newton. So for 20 Newton force, we are considering this one. So I am writing first for 20 Newton force. We will get the data, this area, this is 20 Newton. So the question is saying that as shown in the diagram, with what force is the spring pulled? With what force is the spring pulled? This is the pivot. First we have to find this one for 20 Newton force, and for 20 Newton force, torque is equal to F cross D. F is given as 20 Newton, and D is given as 40 centimeter. So 20 into 40 Newton centimeter, and that will be equal to 800 Newton. So we are writing it 800 Newton. Ladies and gentlemen, now for the second part, and they are saying for 160 Newton, because they given us that the uh, F for 5 Newton. So as torque is equal to F cross D, so F is given as uh, we have to find torque is given as 800, and we have to find F, and then D is 5 centimeter. So this implies that F is equal to 800 divided by 5. So 160 Newton is the answer of this, and that is the option D. So in this case, option D is the correct one. Option D. Now third number question is very important question. They given us a stick bar which is not uniform. The figure is given and the question is saying a non-uniform rod is balanced as shown in the diagram. Given that the center of mass of rod is 40 centimeter. Yes, so 14 centimeter from the end of mark A. What is the mass of the rod? Ladies and gentlemen, there are two torques acting on this bar. One is due to the weight attached, yani this one, which is 80 gram. This is also producing a torque to the bar. That is, torque is equal to 80 multiplied by 20, because this from this trestle, this one is what, 20 centimeter it is given to you, and this is the clockwise moment, this is the clockwise rotation. One is due to this bar. The second torque which is acting on this is due to the weight of the bar which act at the center of mass. The weight of this bar is, one is this attached weight, one this bar is having its mass as well as its weight. So that is the center, and this is 16 into m. M is that mass which we are representing with the capital M, which we are representing with the capital M. So ta 2 is 16, and 16 is given to us in the 40 and then 16. Okay. Now, as we know, I'm coming here because we don't have as clockwise torque must be equal to anti-clockwise torque for stability. So we are putting the clockwise torque 80 multiplied by 20 and anti-clockwise m multiplied by 16. M multiplied by 16. So m is equal to 80 multiplied by 20 divided by 16, and when we calculate it comes out to be 100 gram. This is the 100 gram, and 100 gram is given as B option. So it means that B option is the correct one. Now the fourth one is given this example, and they are saying whether this will be stable equilibrium, this, because in these three the contact is very small, the base area, so these are not unstable, but if you are pulling it, it will come back to its original position if you are tilting it after certain time. So in this case the A option is the correct one. All other are not stable equilibrium. uh, they are asking that which of the following diagram shows a sphere in stable equilibrium. Now, the final question of these multiple choice questions for today, they given us four shapes, and they are asking the diagram show cross section of four solid objects. Which object is more stable? Because this one is having more area in the contact, this is having less area, this is having very less area in contact to the ground, and this also. So this one will be the more stable one, and that is the B option. Tomorrow we are going a very important section B, which are the structure questions. So don't miss. Subscribe my channel, press the bell icon. Thank you very much for watching. Allah Hafiz.